Hello everyone, this is Sravanthi, working as Assistant Professor, Department of Chemistry in Institute of Aeronautical Engineering. Today we are going to discuss about question bank on engineering materials. So here first question is, explain the sol-gel process for manufacturing of nanomaterials. So how can you prepare nanomaterials on sol-gel process? So here nanomaterials means the materials of at least one dimension. That means it between 1 nanometers to 100 nanometers. The particle size is 1 nanometers to 100 nanometers are known as nanomaterials. So nano means, from the Greek, nano means very small. So the particle size is that means one dimension. It between 1 nanometers to 100 nanometers is called nanomaterials. So how can you synthesize these nanomaterials? By using this sol-gel process. So here in the sol-gel process, the main principle is conversion of precursor. Precursor means starting material. So here the conversion of precursor solution into gel via hydrolysis and condensation reaction. So here the sol-gel method is mainly used for preparation of nanomaterials. Here the main principle involved in this is conversion of precursor. Precursor means starting material, that means sol. So it convert into gel. So sol convert into gel or precursor converted into gel via two methods, that is hydrolysis and two steps, hydrolysis and condensation reactions. So this method is mainly used for preparation of metal oxide nanomaterials. So the sol-gel method is mainly used for preparation of metal oxide nanomaterials. The best example is zinc oxide nanoparticles and titanium oxide nanoparticles, etc. We can synthesize in this sol-gel process. So it is a good example for bottom-up approach. Generally, there are two types of methods are there for preparation of nanomaterials: bottom-up approach, top-down approach. So it is sol-gel method is a bottom-up approach. So it is a wet chemical technique. Here we are using water, solvents. So it is a wet chemical technique. So here in the sol-gel method, we are preparing metal oxide nanomaterials. So in this, what is the main principle involved in this? Conversion of precursor, that means sol, into gel via hydrolysis and condensation reactions. So what are the steps involved in this preparation or synthesis of nanomaterials? So here the following steps are involved in the synthesis of nanomaterials in this by sol-gel process. So first step is preparation of sol. Preparation of sol. So in this method, metal alkoxide, it is a precursor. Metal alkoxide used as a precursor, that means starting material. So this metal alkoxide used as a precursor to synthesize nanoparticle of metal oxide. So your starting material is metal alkoxide. So it is used as, acts as a precursor. So it is used for to synthesize the nanoparticles of metal oxide. So in the sol-gel method, already we know that synthesis of metal oxide nanoparticles or nanomaterials. So here how can we synthesize this metal oxide nanomaterials? So the first step is preparation of sol. So in this method, metal alkoxide is used as a precursor to synthesize nanoparticles of a metal oxide. So in this, first metal alkoxide is dissolved in alcohol. Metal alkoxide acts as a precursor. So it is dissolved in alcohol and then add water. So under acidic, basic or neutral conditions. So here addition of water, it leads to hydrolysis. So it followed two steps. What is that? Hydrolysis and polycondensation reactions. So in this first step, preparation of sol, it's involve hydrolysis. That means precursor. That means metal alkoxide dissolved in alcohol by adding water. So the condition is acidic or basic or neutral conditions. So when we are adding water, it leads to hydrolysis in which alkoxide ligand is replaced with hydroxyl ligand. So alkoxyl ligand replaced with hydroxyl ligand. This is salt preparation via hydrolysis process. And next step 2 is conversion of salt to gel. First step is preparation of salt by adding alcohol and water. Now second step is conversion of gel. So here the polycondensation reaction between, so it's involved 2 steps. So what is the first one is hydrolysis. So in this hydrolysis reaction we prepared salt. So next one is polycondensation. So here conversion of salt to gel. So the polycondensation reactions between MOH, metal alcohol and metal alkoxide. So here MOH and MOR result in the formation of oxide, that means metal oxide metal bonding, or alcohol MOHM. So bridge network gel, this is a gel formula. So the polycondensation reaction between metal alkoxide and metal alcohol. So in this case it forms a gel, it converts salt into gel. So that leads to increase in viscosity of the solution. So first we are taking solvents, that means metal alkoxide dissolved in alcohol and water. So in this case it forms salt. When it converts to gel, the thickness, that means viscosity of this gel is increased. So here MOH and MO, metal alkoxide and metal hydroxide, undergoes polycondensation reaction, then form gel formation. Like via MOM or MOHM bridge network, gel is formed via polycondensation reactions. So in this diagram, first one, precursor. So that means starting material like metal alkoxide. Here we used as a precursor. And also adding solvent, that means alcohol. This metal alkoxide dissolved in alcohol and adding water. So in this case it forms salt formation. It forms colloidal structure in salt. That means oil in water, that is structure is formed in this. And after that polycondensation reaction, the viscous salt converts to gel. That means the thickness of the solution is increases. Next, this gel is supercritical drying. That means critical temperature we are heating, it forms aerogel. Or it is isolated with the thermal temperature, at high temperature, 800 degrees centigrade. So in this case it forms aerogel. Or freeze drying, it forms cryogel. So finally you will get nanomaterials, nano products, metal alkoxide. Generally we synthesize metal oxides in this salt gel process. So next, third step is aging of the gel. So the reaction mixture is allowed to continue polycondensation reactions until the gel transforms into solid mass. So that means completely evaporate of solvent. So completely evaporate of solvent. That means the reaction will still continue of polycondensation reaction in between that metal alkoxide and metal hydroxide. So in this case completely evaporate of solvent, that means it converts to solid mass. Gel converted to solid mass. And next step is removal of solvent or drying of gel. So here the water and other volatile liquids are removal from the network. So we can remove the complete solvent or water or any volatile liquids present in this solid mass. We can remove in this process. So here this is isolated by thermal evaporation. So the resulting product is termed as zero-gel. Just now we discussed already. So this polycondensation reaction continues still. So then in that case we can remove the solvents which are present in that sol, so that means gel or solid mass. So here that solid mass is isolated by thermal evaporation. So the resulting product is called as zero-gel. And if the solvent is extracted under supercritical conditions, so here the resulting product is named as aerogel. Aerogel. And final step is heat treatment. So here the sample obtained is calcinated at high temperature. So whatever after completing the first 4 steps, so the remaining sample heated at high temperature, that means 800 degrees centigrade temperature, to obtain nanoparticles. So these nanoparticles formed by salt gel process commonly have a size ranging from 1 to 100 nanometers. 1 to 100 nanometers. So here starting material is acts as a precursor. When we dissolve in this by adding alcohol and water, then it converts to solution. So after polycondensation reaction continue between metal oxide and metal hydroxide, then salt converted to gel. So rapid drying it forms aerogel. And it is isolated thermal temperature then form zero-gel. So finally we obtain nanoparticles or nanomaterials or nanopowder synthesized in this by salt gel method. So what are the advantages of salt gel process? So the main advantage of salt gel process are high purity of the product. We get high purity of the product and the narrow particle size distribution and the achievement of uniform nanostructure at low temperature. But what are the disadvantages of salt gel process? So the cost of raw materials, that means chemicals which are used for the preparation of these nanomaterials, may be high. Next, what are the applications of the salt gel method? So the materials obtained from the salt gel process or salt gel method that are used various optical, electronic, energy, surface engineering and biosensors and pharmaceutical and separation technology such as chromatography. We are using this nanomaterial which are synthesized by salt gel process. So in this way we have to prepare the nanomaterial synthesized by salt gel method. And next question is in this chapter engineering materials. So discuss the composition, setting, hardening reactions of Portland cement. So here what is the chemical composition of Portland cement? So Portland cement is chemically defined as a finely ground mixture of silicates and aluminates of calcium of various compositions. So it is a combination mixture of silicates and aluminates of calcium of various compositions. So approximately chemical composition of this Portland cement is, so here dicalcium silicate, tricalcium silicate, tricalcium aluminate and tetracalcium aluminoferrite, calcium oxide, magnesium oxide and calcium sulfate. So what is the formula of dicalcium silicate? 2CaO-SiO2. Tricalcium silicate, 3CaO-SiO2. Tricalcium 3 silicate SiO2 symbol. And tricalcium aluminate. Tri means 3. So 3CaO aluminate formula Al2O3. And tetracalcium aluminoferrite 4CaO Al2O3 Fe2O3. And calcium oxide CaO. Magnesium oxide symbol is MgO. And calcium sulfate is CaSO4. So these are the formulas of what are the main compounds which are used for the preparation of Portland cement. So here dicalcium silicate symbol is C2S and tricalcium silicate symbol is C3S. Tricalcium aluminate C3A and tetracalcium aluminoferrate C4AF. The shortcut symbols which is used for write on the reactions, it is important. And next, how much percentage of these compounds used in this preparation of Portland cement? What is the composition of all these main components which are used for the preparation of Portland cement? So dicalcium silicate, it is used 25% and tricalcium silicate 45%, tricalcium aluminate 10% and tetracalcium aluminoferrite is 9% and calcium oxide is 2, magnesium oxide is 4 and calcium sulfate is 5. So this is the composition of various components of calcium, silicates and aluminates of calcium we are taking for the preparation of Portland cement. This is the composition of Portland cement. Next, setting and hardening of cement. So in the cement, when mixed with water, it forms plastic mass is called cement paste. See this image here. So cement when mixed with water, it produces plastic mass is called cement paste. So during hydration reaction, gel and crystalline products are formed. During hydration reaction, which type of products are formed? Gel, tobermonite gel, that means, and crystalline products, calcium hydroxide, like that. So gel and crystalline products are formed. So the insoluble gels and crystallines have the ability to surround inert materials like sand, bricks, crushed stones, etc. So this process of solidification comprises of setting and then hardening. So what is the meaning of setting? So it is defined as the setting of the original plastic mass due to the formation of tobermonite gel. Due to the formation of tobermonite gel. That means when we are mixing with water to cement, it produces plastic mass. This is called setting. So in this case, the product is called tobermonite gel. The plastic mass formed, that is mainly due to the presence, due to the formation of tobermonite gel. This is called setting. And what is the meaning of hardening? So here it is defined as the development of strength due to the formation of crystals like calcium hydroxide. Here, see this here, hardening means a development of strength due to the formation of crystalline compounds. So this is setting and hardening. Setting means it provides plastic nature due to the presence formation of tobermonite gel, but in this hardening it provides strength, that means due to the formation of crystalline compounds. So the setting and hardening of cement is due to the formation of interlocking crystals reinforced by rigid gels formed by the hydrolysis or hydration of the constitutional compounds. So what are the reactions takes place in this setting and hardening of cement? So here day 1. So it takes time is 1 to 28 days after completion of the setting and hardening process. So day 1 reaction is when the cement is mixed with water. When the cement is mixed with water. So at first hydration of tricalcium aluminate. Generally composition of Portland cement we are using tricalcium aluminate, dicalcium silicate, tricalcium aluminate and tetracalcium aluminoferrate, calcium oxide, magnesium oxide, calcium sulfate. So many different types of compositions of bogie compounds add in. So here, so in day 1 reaction, when we are adding water with cement, here at first hydration of tricalcium aluminate. So which one is hydrolyzed? All the bogie compounds which are used for the preparation of Portland cement. So in this case, first one is tricalcium aluminate hydrated. So when we are adding water to cement, first day immediately reaction of tricalcium aluminate. So it takes place rapidly within 1 day. So and the paste becomes quite rigid within a short time. So which is known as initial set or flash set. So here tricalcium aluminate, when we are adding water, first day immediate reaction of tricalcium aluminate, hydration of tricalcium aluminate, then form hydrated tricalcium aluminate crystalline compound is formed. Your strength of that compound is 880 kilojoules per kilogram. And here, in order to retard the rapid hydration of tricalcium aluminate, so just now we discussed already. So when we mix water to cement, so immediately tricalcium aluminate is hydrolyzed. So it is retard, delay. That purpose we are adding calcium sulfate, that means gypsum. That means here gypsum acts as a retarding agent to avoid the quick setting of cement. So in order to retard the rapid hydration of tricalcium aluminate, that means early initial setting, so gypsum is added during grinding of cement clinkers. So here gypsum reacts with tricalcium aluminate to give insoluble calcium sulfoaluminate. Insoluble calcium sulfoaluminate complex is formed. So which does not possess hydrating property and retards early setting of cement. So when we are adding water to cement, at first day, immediately tricalcium aluminate is hydrolyzed. So it can be delayed by adding retarding agent like gypsum. So here gypsum acts as a retarding agent, delay for quick setting. So here retards early setting of cement. So that purpose we are adding this gypsum to this tricalcium aluminate. So here it forms the insoluble calcium sulfur aluminate complex. So here does not possess hydrating property and retards early setting of cement. This is day 1 reaction. And next day 2 to 7. So after the hydration of tricalcium aluminate. So immediately hydrolyzed is tricalcium silicate begins to hydrate to give tobermonite gel. So after the hydrolysis of first day completed. So in first day which one is hydrolyzed? Tricalcium aluminate. So in day 2 to 7 in between that which one is hydrolyzed? Tricalcium silicate. So after hydration of tricalcium aluminate, tricalcium silicate begins to hydrate. So to give tobermonite gel and crystalline compounds. So this is responsible for the development of initial strength of cement. It is responsible for development of initial strength of cement. So the hydration of tricalcium silicate, which gets completed within 7 days. But tricalcium aluminate hydrolyzed within 1 day, but tricalcium silicate hydrolyzed within 7 days. So it does not contribute much to the strength of cement. So the strength of this product, this composition is 500 kilojoules per kg. So your tricalcium silicate hydrolyzed in day 2 to 7 in between that. So it forms tobermonite gel and crystalline compound, provide the initial strength of cement. It is the initial development of initial strength of cement. But it does not contribute much to the strength of cement. And next day 7 to 28. So in between that is day 7 to 28, dicalcium silicate. Dicalcium silicate reacts with water very slowly and gets completed within 7 to 28 days. So this dicalcium silicate hydrolyzed, then it gives tobermonite gel and crystalline products. So here the increase in strength between 7 to 28 days due to the formation of tobermonite gel and crystalline products of both tricalcium silicate and dicalcium silicate, C2S and C3S. So in that period the strength of the cement is increases due to the formation of tobermonite gel and crystalline products. And in that period only, so the hydration of tetracalcium aluminoferrite. Tetracalcium aluminoferrite takes place initially. So the hardening takes place finally through crystallization along with dicalcium silicate. Along with dicalcium silicate. So here tetracalcium aluminoferrite hydrolyzed, then it forms hydrated tricalcium aluminate. So the final setting and hardening of cement is due to the formation of tobermonite gel and crystalline products of calcium hydroxide and hydrated tricalcium aluminate. So this is setting hardening of cement. And next question is in this module engineering materials, what should be the flash and fire point of a good lubricant? So first, what is the meaning of lubricant? So lubricant is a substance used in between two moving surfaces. So what purpose we apply lubricant in between two moving surfaces? To reduce the friction. To reduce the friction by adding this lubricant in between two moving surfaces. So what is meaning of lubrication? So lubrication is a process. So it reduces the friction and wear between two moving surfaces by adding lubricant in between them. So when we are adding lubricant in between two moving surfaces, it reduces the friction. So this process is called lubrication and that substance is called lubricant. Best example, oils, grease, Vaseline, all these are the lubricants to avoid the friction. Now how can we determine the flash point and fire point of a lubricant? So flash point means it is the lowest temperature. So at which temperature oil gives enough vapors that ignite for a moment when a small flame is brought near to it. So that point is considered as flash point, fire point. So it is the lowest temperature. So at which temperature oil burns, oil gives enough vapors and burns at least 5 seconds when small flame is brought near it. So generally the fire point is 5 to 40 degrees centigrade higher than flash point because it is continuously burn at least 5 seconds. So what is the significance or importance of flash point and fire point? So the knowledge of flash point and fire points is useful in providing protection against fire hazards during transports and storages. So here lubricating oils of paraffinic base, it possesses higher flash point than those of naphthalenic base. So hence the determination of flash point and fire points helpful is identifying the type of lubricating oil. So good lubricant always should have high flash and fire points higher than operating temperature of the machine. Operating temperature of the machine. So good lubricant should have flash and fire points higher than the operating temperature of the machine. So how can we calculate this flash point and fire point? How can we determine? So here flash point and fire point determination purpose we are using same apparatus. So here an oil is heated in a prescribed rate in open cup or closed cup. Open cup or closed cup. Prescribed amount of oil we are heating in this taken in this open cup or closed cup apparatus standard dimension. So during heating process, during heating process it produces vapors. So a small flame is periodically applied over the surface of the oil. A small flame is brought near this oil. So in this case, this oil gives enough vapors and ready to catch the fire. Ready to catch the fire. That is called flash point. Fire point means it continuously burn at least 5 seconds. That is called fire point. So a small test flame is periodically applied over the surface of the oil. So the temperature at which distinct flash is seen is the flash point. That means it is ready to catch the fire. So that is called flash point. So the heating and periodical application of test flame are continued. So the temperature at which the oil vapors catches the fire and burns continuously is the fire point. So the viscosity of oil can be determined by Redwood viscometer and Ostwald's viscometer or Seaborg viscometer. So this is a Redwood viscometer which is used for the determination of flash point and fire point. And next question. What are the thermoresponse materials? So explain the preparation properties and uses of polyvinyl amides. So here these are the thermoresponse materials. That means temperature. So these materials respond at temperature. So these materials, they are changing their properties with respect to temperature. So these are the polymers that exhibit drastic and discontinuous changes in their physical properties with temperature. So these materials change their properties, physical properties, change with temperature. So this type of materials are called thermoresponse materials. They are response with temperature. They are changing their properties with temperature. So it's called thermoresponsive materials. So the thermoresponsive polymer are class of smart materials. They are the class of smart materials. That means that have the ability to respond a wide change of temperature. Wide change in temperature. So property that makes them useful material in wide range of applications. So that's why we preferred in so many application point of view, we prefer these thermoresponsive materials because they change their properties with the temperature. So the review focuses mainly on the studies published over the last 10 years on the synthesis and use of thermoresponsive polymers for in which field they are preferred. There is research on this thermoresponsive polymers, biomedical applications, that means it's including drug delivery, tissue engineering and gene delivery. So these polymers respond, they change their physical properties with temperature. So this type of polymers are called thermoresponsive materials. So this it is having this type of property. That's why we prefer so many medical application purpose we are using. Research also where you prefer these polymers. So best example of thermoresponsive polymers are polyvinyl amides. So in all the thermoresponsive polymers, so polyvinyl amides and poly-N-vinyl caprolactam is a well-studied temperature responsive polymer. It is the most preferred first polymer, polyvinyl amide, and second one is poly-N-isopropyl acryl amide. Poly-N-isopropyl acryl amide. It's also called NIPAM. So the most popular temperature responsive polymers, these two are. So here the polymer shows similar lower critical stabilization temperature behavior in water between 30 to 32 degrees centigrade. 30 to 32 degrees centigrade. So here the synthesis of poly-N-vinyl caprolactam polymer by free radical polymerization by using modified version of the protocol. So here polyvinyl amides. So what is the thermoresponsive properties of polyvinyl amides? So here in this we discussed mainly most important popular thermoresponsive polymer is poly-N-vinyl caprolactam. It is an example of polyvinyl amide. So with thermoresponsive behavior. So it exhibits a similar LCST, lower critical stabilization temperature, as NIPAM, making it soluble in water below LCST and insoluble above it. These are thermoresponsive properties of polyvinyl amides. So what are the applications of this polyvinyl amides or thermoresponsive polymers? So these polyvinyl amides are used in various applications including drug delivery systems, flocculant, and in the formulation of responsive coatings. So we preferred in that case drug delivery systems mainly. So in this session we'll learn about what are the important questions in these engineering materials. So I hope understood all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.